Good afternoon. So today we are going to look at the way that we can calculate the area under a curve when that curve is an actual curve and not just a straight line. We're going to use the concept that we learned about displacement in the unit on kinematics, where we calculated the displacement using the antiderivative, and we also calculated the displacement using the area under a graph. Let's look back at finding the displacement from a velocity versus time graph. If we have a constant velocity and the object undergoes that constant velocity for a time interval, delta t, then clearly the displacement must be that velocity times delta t. But if you look at the graph of that, well, that's just the area underneath the velocity graph. If the velocity is negative, then it's a negative area, meaning it's a negative displacement. But it's simply the area between the velocity graph and the horizontal axis. So let's see how you would find the displacement if you had multiple constant velocities, one after the other. Let us say that our object moves with velocity v1x for a time interval delta t1 and v2x for time interval delta t2, etc. Then the displacement would be v1x times delta t1 plus v2x times delta t2 plus v3x times delta t3, etc. Graphically, we would show it like this. Clearly, the displacement is just the sum of all of the little rectangles showing the individual displacements over each of the time intervals. In summation notation, we read it like this. The displacement is equal to the sum from 1 to n of vix delta ti, where I is what goes from 1 to n. The total displacement then is the sum of all those individual rectangles. So what can we do when our velocity is not a step function like that, but changes continuously? Say something like this. Here we have a velocity that changes smoothly from time t1 to time t2. And we want to find out the displacement over that larger time interval. Well, we could approximate it simply by breaking our time interval from t1 to t2 up into smaller time intervals, delta t1, delta t2, delta t3, etc. And then we would just have to add the area of those little rectangles. The base of the rectangles is formed by the time intervals, delta t1, delta t2, etc. And the height of the rectangles is given by the average value of the velocity over that interval. So that's what we're going to call v1, v2, v3, etc. Now, just as before, the total displacement is just the sum of all those individual little areas. Now, as you can see, there's going to be some error in this process because the velocity is not constant over each small time interval. So there's a little bit of extra rectangle, extra triangular piece that you'd be adding in there that shouldn't be there, or another triangle piece that you should take out. But if you make the interval small enough, then you can get a really accurate estimate of what your displacement is. In fact, if we use very, very small intervals of time, a differential is sometimes called, we can get extremely close to the area under the curve. In fact, if we use infinitely small areas of time, if you will, or almost infinitely small, then we can get arbitrarily close to the area under the curve. Mathematically, what we're going to do is we're going to replace our intervals delta t with a very small interval dt. And instead of that summation symbol, which is just the Greek letter sigma, stands for sum, we're going to use a s symbol. That smooth integral symbol, it's sometimes called, or S symbol, just also means a sum, but it's a sum over very tiny intervals. Now, how do we calculate that, though? We're going to try to go from a finite sum to an infinitesimally small interval sum. Well, how do we calculate that? Well, we already know, because we already know how to calculate for certain functions what the displacement is. Now, this quantity is called the definite integral, and it means the area under the curve using a very, 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 very small interval from the lower limit to the upper limit. You see the way it's written there? You see the summation symbol has been replaced with the S symbol. And you see on the bottom half of the summation symbol, we put the lower limit of what we're trying to find the area under, and at the top of it, we put the upper limit of what we're trying to find the area under. So we're trying to find the area underneath that graph. But we already know how to do that. The displacement, given the velocity, we already know how to calculate that. We know that the velocity is the derivative of position. So the position is the antiderivative of velocity. Now there's going to be some constant of integration there, but since we only care about the displacement, we don't have to worry about that constant that we get when we take an antiderivative. We just simply calculate the position at time t1 and the position at time t2 and subtract them. And that constant will then be subtracted out, and the difference between those two positions is the displacement that we want. So for example, let us say we had this. Let us say our velocity function was 3t squared. That means that our position function must be something like, well, we know how to do this. Take the antiderivative of a power function. So the antiderivative of 3t squared would be t cubed plus c. The displacement then would be from time t1 to time t2 would just become t2 cubed minus t1 cubed. The displacement then, which is represented by the area under the velocity versus time graph, is the difference of the antiderivatives of the function evaluated at the two endpoints. So the definite integral of a function gives the area under the curve, and the definite integral is equal to the antiderivative of the function evaluated at each of the two endpoints. In other words, the definite integral of the velocity function over the time interval from t1 to t2 is equal to the antiderivative of the velocity function, which is the position function, evaluated at t2 minus the antiderivative evaluated at t1. This fact that the definite integral, which is the area under the curve, is equal to the difference of the two antiderivatives of the endpoints at the endpoints is called the fundamental theorem of the calculus. Now, we're not going to prove this per se. We're just going to take it and use it. You will do this in calculus if you have not already done it. And if you have interest in finding out what the exact proof is, if you got it from last year, well then, please be sure to ask Coach Myers. Now, so far we have only calculated the antiderivatives of power functions. So the definite integral for a power function is something that we know how to calculate. The definite integral of a function of the form c times t to the nth power dt is equal to c times t to the n plus 1 power divided by n plus 1 evaluated at each of the two endpoints and then subtracted. You can see why sometimes in calculus class they don't quite explain exactly why you have to put that little dt in there. What does that little dt mean in the definite integral? Well, that is meaning that we are trying to calculate an area using very, very, very small intervals of time in this case. Let's do some examples for practice. In each one of these, I'm going to have you assume that the object starts its displacement at time 0, and then it moves through with the given velocity function until a time later of t. In other words, you're going to try to calculate what the displacement is at some time t later if the time interval starts at 0. Here's your first example. Calculate the displacement if the velocity function is just 6, a constant 6, and the time interval is from 0 to time t. Go ahead and stop the video now, and then once you have an answer, start it back up again. Now we know this one should be just the constant velocity time to time. We already knew how to do that one before. So let's do a harder example. Here your velocity is 4t, so in a constant acceleration then. This one should also be familiar to you, but let's go ahead and do it. Stop the video, and when you have an answer, go ahead and start it back up again. So your displacement should be 2t squared in these situations. Okay, let's do a slightly harder one then. Here our velocity is 3t squared. So what is the displacement over the time interval from 0 to t if that is our velocity function? Go ahead and stop the video now and then start it back up once you have your answer. So here we had to take the antiderivative of 3t squared, which became 3t cubed over 3, or just t cubed, and we had to evaluate that at the endpoints. So we had to evaluate it at t and at 0. The 0 went away, leaving us with t cubed. And one more for good measure. If your velocity function is 8t squared plus 5, and you want to calculate the displacement over the time interval from 0 to t. Go ahead and try this one, and then start the video up again once you think you have the answer. Now, it's not exactly the distributive property, but a property of integrals is that you can integrate each term in a sum separately. So, or you can think of it as taking the antiderivative of the sum. Either way is appropriate. What you end up here then is the antiderivative of 8t squared, which should be 8t cubed over 3, and the antiderivative of 5, which should be 5t, evaluated at the two endpoints, which is 0 and t. The 0 still goes away in both terms, and so what you are left with is 8/3 t cubed plus 5t.